All right, welcome everyone. This is the second video in topic 1 here on ideal gases. Here, I'm going to talk a little bit more about where the ideal gas law came from, such as kind of a review probably from general chemistry. Right. So one of the ways you can get to the ideal gas law, which originally was obtained, was through empirical observation. Right. Start off with things like Charles' law, where right, when you just change volume and temperature or pressure and temperature, right? You keep either pressure and number of moles constant or volume and number of moles constant. You see this linear relationship, right, between pressure and temperature and volume and temperature. Okay. Right, imagine here having like a balloon, putting it in a freezer. That balloon will shrink. The pressure is the same. Right, number of moles are the same, but you decrease temperature, and the volume of that balloon will decrease. Okay. Right. Then you have Boyles Law, where you keep temperature constant, number of moles constant, and you find that pressure times volume ends up giving you a constant. Okay. And so that they're inversely related with each other. Right. And then there's Avogadro's law, which showed that as you increase the number of moles of gas, you got an increase in volume, okay, at constant temperature, right? And when you combine all those laws together, you get the ideal gas law. PV equals nRT, okay? And so what's plotted here in this slide is a three-dimensional plot of pressure versus volume versus temperature. Okay? And that surface that's plotted there, that surface tells you what possible states a gas can exist at. Anything off of that surface is impossible for a gas to exist. Okay? So any pressure, volume, temperature combination that is not on that surface will never occur in the real world, assuming some constant number of moles. Okay, now we can split this surface into different lines, right? If we look at constant temperature cases, right, this is considered isothermal, right? And then you can look at what happens under constant temperature and what those look like, okay? That constant temperature line, right, is given here, okay, right? And then you have constant pressure cases, right? Isobaric, right, that, for example, is given here, okay, and then you can have constant volume cases, right, that's kind of given here, okay. So you have these different lines that appear on the surface related with constant temperature, pressure, or volume situations, okay. And we'll often use in this class talk about isothermal processes, isobaric processes. And often we say constant volume instead of like isochoric or something like that. Okay. All right. Just kind of a review here of how we can use the ideal gas law to get molecular weight from density. Okay. Right. So if we start with our ideal gas law, we use the fact that the density, right, rho is equal to mass divided by volume, okay? And the fact that the mass is just equal to the molecular weight, which I'm using as capital M here, times the number of moles, okay? So if I combine equations 2 and 3, I get that the density is equal to the number of moles times the molecular weight divided by the volume, okay? If I rearrange that in terms of the volume, I say volume equals the number of moles times the molecular weight divided by the density, right? And then I just plug that into equation 1, right? You'll get that the pressure times the number of moles times the molecular weight divided by the density equals nRT, okay? Then you rearrange that, simplify, you find that the molecular weight of a gas is equal to the density of that gas times R times T divided by the pressure. And this relationship is true for any ideal gas, right, satisfies this relationship between its molecular weight and its density as a gas. Okay. All right. Well, often when describing gases and even liquids and things like that, talking about molar volume. Okay. Molar volume is the volume per mole that is occupied by some sort of substance. Okay. And often obtained by doing volume divided by the number of moles, right? So for our ideal gas law, right, PV equals nRT, right? Solving for volume over N, you get RT divided by P. Well, volume over N is just a molar volume, okay? So the molar volume of an ideal gas is just RT divided by P. All right, for mixing of gases, we'll start here with Dalton's law, which is true only for ideal gases. And for Dalton's law, you're assuming that the intermolecular interactions between molecule A and molecule B are the same as they are between themselves, right? Or that they just don't have any intermolecular interactions between each other, right? Because in that case, the total pressure will just be the sum of the partial pressures of those different gases as if they were alone, okay? Because adding the gases together, right? If the gases don't interact with each other, then they don't really see each other, they don't care about each other, and so the total pressure is just the sum of the partial pressures of those different gases. Okay. Now, under a constant volume and temperature system, right? Right. If I have P total equals P1 plus P2, plugging in for those pressures, we get nRT, this is total over V, equals N1 RT over V plus N2 RT over V, okay? Right, and RT and volume all cancel, right, and you just get the total number of moles is just right, equal to N1 plus N2, right? Which is what we'd expect, right? Sum of the moles of each gases gives you the total number of moles. And that is true no matter what the gas, real or ideal. Okay. So again, that's true for all gases, right? I can rewrite that equation by dividing by the total number of moles and writing things in terms of mole fractions, right? Mole fraction, xi here, is related with the number of moles of I divided by total number of moles. And so you get, right, that 1, right? So divide this equation by n total, and you just get 1 equals the sum of all the different mole fractions, okay? And you can use the relationship of the mole fraction in the gas phase such that the partial pressure of I is just related to the mole fraction of I times the total pressure. And that is another way to relate the partial and total pressure to gases, or of a gas in a mixture, okay? And so that's going to do it for kind of today's discussion of ideal gases and mixing of ideal gases. Next, we'll talk about another way we can get the ideal gas equation, as well as then start talking about real gases.